Medieval mathematics and mathematics of Renaissance. Two time periods that follow each other back to back, but so very different, with such different human achievements and such different developments in culture, religious, and science of mathematics. First of all, let's define the timeline. The Middle Ages, also called as Dark Ages, is the period, in European history in particular, between the fall of Roman Empire, 500 AD, and the beginning of Renaissance, the rebirth, in 1400s. The names themselves suggest what happened, Dark Ages to rebirth. The Dark Ages are really characterized by very little happening between sciences and mathematics and any kind of intellectual achievements. They are characterized by wars, the political and religious turmoil. Nearly 1,000 years went between those two times. No wonder some scientists believe that Middle Ages were made up. So very little actually happened in terms of human development. What is interesting to witness through the times is the spread of 5 major world religions through the time. Notice here that the timeline at the bottom goes at constant speed. It moves fairly quickly, but nonetheless. So up until now, we see the development of Hinduism and a little bit of Judaism, but various world events, the births of various leaders, spawn new religions. And then once we hit the positive, so we're just past the era Jesus has been crucified, we see the spread of Christianity throughout Europe, and this is where we enter into the Dark Ages. Not much is happening in Europe, the various Spanish conquests and so on, while the Islam spreads through the Asia and the southern of Africa. And then once we enter into the Renaissance, the Islam moves in a little bit more southwards, the Christianity goes a little bit further east, and then of course the age of discovery begins, bringing Christianity to North America. And while the religions, in some sense, spread and stabilize throughout the world, we still see pockets of different religions in between the ones that have occupied large areas. So, for example, we see a little bit of Hinduism in South America. We see pockets of Christianity and Islam in Asia. As the spread of religions took over European continent, the materials available for learning consisted of many religious texts, highly illustrated with biblical and Christian stories. The mathematical materials, for example, consisted of various abacus, something that would be good enough for everyday calculations. And the beginnings of thinking about nature and what constitutes a human being started coming into light, but a lot of this was surrounded by the mystery of the stars, the zodiac signs, the astrology, not so much as astronomy, was subject that humans were interested in at this point in time. A lot of this was mystical and not tried even to be understood. A lot of mathematics was procedural, consisting of tables of values to be looked up for specific calculations, such as constructions and architecture. Very little, if any at all, attention was paid to the mathematics as science, as the subject, and many other sciences were treated very similarly in the most mundane way, only for their applications to everyday lives. The stagnation of mathematics in medieval times is hard to deny. The catalyst for change was the reconquest of Toledo in 1085 that was previously occupied by Islamic kingdom and now was conquered by the Spanish king Alfonso VI. Fortunately, Alfonso VI decided not to destroy the intellectual properties that were present in Toledo, which meant that it became this huge center and a great undertaking of translations of Greek works into Latin. It is only once these translations were made and the Greek works were available to the Christendom that the medieval Europe really began developing its own mathematical capabilities. The Renaissance, the rebirth, was really started by the rediscovery by the Europeans of the Greek works. One of the reasons I'm showing you different pieces of art throughout is to also witness the progress of how things were depicted. Medieval works of art are, if anything, characterized by their two-dimensionality. These are the types of things where three-dimensional objects were drawn very flatly. But as we move forward, we see more realism come through the various pictures. And with that, actually, at the same time, we see more and more interest in nature, in where humans come from, how they're built, and how they're constructed. With that comes various developments in mathematics and thinking about mathematics. Roger Bacon, all science requires mathematics. The knowledge of mathematical things is almost innate in us. It's the easiest of science, a fact which is obvious in that no one's brain rejects it. For laymen and people who are utterly illiterate, know how to count and reckon. Count and reckon. Not just count, but also apply logic to things. Here he's pictured with the universe, with how medieval people actually viewed the universe and the motions of the planets. Remember that Copernicus was also still criticized for his understanding of the universe. The one notable progress in mathematics was made, and in particular by Italian mathematician Fibonacci, in his introduction of Arabic numbers into Europe. These are 9 figures of the Indians, the Hindu Arabic numbers. With these 9 figures and with the sign 0, which has not been present in every numerical system up until now, which is in Arabic called Zephyrium, any number can be written, as will be demonstrated. And in his work, in Fibonacci's work, he actually does go through defining the system and showing examples of its use. Many of us, of course, know Fibonacci not just for the introduction, or rather, likely not for the introduction of Arabic numerals to Europe, but rather for the Fibonacci numbers, for the sequence that he has developed to describe a recursive process. And here is the page of his work that describes that exact sequence. This sequence again confirms this particular interest now in mathematics as a natural science, how the patterns of Fibonacci numbers occur in a variety of natural phenomena, in the number of leaves and how they're formed, and in general formation of patterns in the nature. So the Fibonacci spiral can be seen throughout. It can be seen in hurricanes as well as shells, as well as, of course, various other domestic creatures. And the Fibonacci numbers are, of course, now found to be parts of the proportions of the human body, which here you can see in Da Vinci's work, which came years later. The other progress in mathematics was made by French mathematician Nicole Oresme, who actually started to study plane and the coordinate systems, was the first one to introduce the idea of a graph and the coordinate system to be put on top of it, how a uniform quality can be represented by a horizontal line. Other than that, once again, we're seeing a bit of a progress in terms of art and how it is depicted to be more and more realistic. And this is the beginning of the Renaissance, with its beautiful realistic paintings, the huge flourishment of art and science and innovation. Here we have Phyllis proving in a tale to Aristotle that a woman's charm can overcome even the greatest philosopher's intellect. Renaissance can be thought of as purely artistic time, but let's take a look at some of the most famous art pieces with a mathematical eye. Here's Michelangelo's David. Michelangelo, known for his genius of sculpting things out of marble and for his precision to human proportion, do you notice anything not proportional about David from this particular angle? Take a look. Once I point it out, it's hard to unsee. But until you notice, it might be a little subtle. In particular, for example, this hand seems a little too big for his body. Michelangelo, who was known for his study of proportions, couldn't have made that as a mistake. So was it intentional? We have to think about what Michelangelo's audience was, or rather where it was located. David was to be put on top of an actual building. So as far as Michelangelo was concerned, David, pardon my depiction here, was to be viewed by people at the bottom of a building. David's proportions were to be seen properly from somebody looking from 50 to 70 feet below. If his hands were any smaller, they would not be visible or they would not seem proportional from the bottom. David was not to be viewed straight on face. He was to be viewed from the distance. From the distance that was vertical. Michelangelo, in his genius, adjusted for those proportions. Here's another masterpiece, Pieta, which is now at the entry of St. Peter's Cathedral in Vatican. Pieta, a Madonna here holding her son Christ in her hands, of course is depicted as too young for what age she was supposed to be, but it is to highlight her innocence. Without talking much about the artistic beauty of this piece, and just mentioning quickly that this is made out of marble, yet depicts folds in fabric that are too realistic to really even imagine being possible to be built out of stone. But think about proportions here. What do we notice in this particular piece? If you think about this, these are supposed to be two human beings, she probably smaller than him, yet she's holding a fully grown man in her arms, and it looks reasonable. He is too small for her frame, if you really think about this, but this is supposed to highlight his death, his weakness. The proportions are not quite right in relation to each other, but are made to look holistic. And as a piece, you don't notice any disbalance in between the two figures. Michelangelo's genius is not just in the study of proportions, but in his ability to adjust them and to be flexible with them. Da Vinci, of course, is famous for his study of proportionalities within the human body. Here again, we're seeing all kinds of Fibonacci type studies with the entire body and with the face in particular. We are also then moving into the study of perspective, something that is often hidden within the Renaissance paintings, but is a purely mathematical achievement by Durer, who actually spent quite a bit of time thinking about how to represent a three-dimensional object on a two-dimensional piece of canvas so it looks three-dimensional to the eye of an observer. We see this in most of the Renaissance paintings at some level. Here is the famous Last Supper. Do you see parallel lines converge? Do you see how realistic the painting is? Of course, we can draw the parallel lines that are all present in the picture, and we can notice that the actual focus, the way that they're converging, is on the one focus where we would like to pay the most attention to, on Jesus, right in the middle of the actual painting. Back to my favorite painting, The School of Athens, we once again see parallel lines converging, and they converge to where we want our eye to go, where our eye actually goes first without us having much power over it, toward the Aristotelian Plato. Again, does knowledge come from the world of ideas, or does it come from the physical world in front of us? The study of perspective was started by Durer in the Renaissance, and thought of the projections of the objects from the different angles. This is something that, while started in Renaissance, we use widely today. For example, in medical imaging, when the CT scans produce two-dimensional images that are then put together to actually represent a three-dimensional object. We can think of the front view, the side view, the top view, and so on, and putting them together into what constitutes a one solid figure is an entire study of mathematics and the study of space curves. We have a variety of things that we can think about in terms of different projections, different rotations, and different figures. We also can think about not just one-point perspective, like the Last Supper or the School of Athens, but two-point perspective, where you have various foci that the parallel lines actually converge to. The other interesting thing that one has to think about in terms of projections is, of course, the map of the world. We are projecting a sphere. Just to be clear, the Earth is not actually flat. I hope you know that. We're projecting a basically sphere onto a flat plane. How can we do so faithfully? We must make some sacrifices. Mercator projection is the one that we're most used to. This is actually a cylindrical projection. So every point has faithful directions, up, south, north, and so on. Locally, it is very correct, but it distorts things more and more as we move towards the poles. You can see the lines here being distorted. So while it is faithful in the middle, it is really not correct close to the poles. The Peters projection, which now looks all out of whack because we're simply not used to the shapes, actually preserves ratios of areas. So in terms of areas, this is the correct way to project. Compare the two next to each other. So here the Peters one is in green and the Mercator, our familiar one, is in the outline of black. The projection we're used to does not preserve areas at all. So to us, for example, Africa looks much smaller than it actually is, whereas Europe is kind of magnified in terms of ratios of areas. Isn't that odd? What else are we missing with having one type of map projection versus the other? Renaissance time has produced art and mathematics that live to this day and inspire and motivate. This is me, 4 years ago now. If you can, visit with Renaissance and look at the paintings and the sculptures and other works of Renaissance artists with the eye for art, for mathematics, and mathematical art.